Hello class, this is Sanjay Kukadiya. I'm here to present the final project for ADTA 5560 recurrent neural networks for the sequence data. In this project, we will heavily discuss on applying RNN and the LSTM neural networks on the time series datasets. As we see in this particular course, ADTA 5560, we learn a lot about sequence data, recurrent neural networks, and its limitations. LSTM neural network, which stands for long short-term memory neural network, and how it overcomes the RNN limitations. We will use both recurrent and LSTM neural networks for the sequence data. Um, we also learned how the time series prediction of sine wave and stock closing price can be done using the LSTM and recurrent neural networks. And we learned how to apply the TensorFlow and Keras framework for the RNN and LSTM neural networks. The scope of the final project is divided into 7 parts. The first part is nothing but identifying a time series data set which is publicly available. I have selected the consumer price index CPI data set in the light of the latest inflation. Part two, we will build a simple RNN model and apply that to the sine wave time series data set to see how RNN can be used to process the sequence data like sine wave. In part three, we will discuss the core concepts of LSTM neural network and the cell. In part four, we will build the LSTM model and use the CPI inflation data, which I have identified in part one. And in part five, we will redesign the previously created LSTM model to see if we can improve the performance or not. And finally, we will compare the performance of the original LSTM model and the redesigned LSTM model in the last section, and we will conclude the final project. So let's go into the part one. In part one, our objective was to identify a similar time series data set, like stock prices. As we are in the middle of heavy inflation across all the categories, I have thought to identify a CPI, the Consumer Price Index dataset, which is publicly available on this website called datasource.capsarc.org, and provided the direct source of the link. But the interesting side on the right hand side is, as you can see, the screenshot of a gas station with in the Beverly Hills, California, which shows the gasoline price as of November 7th, which is last year, which is even lower than today in the light of Russia's attack on Ukraine. But as we can see that in last couple of years, gasoline and any other price indexes are shot to severely high. On average, we have seen 20 to 30% increase in most of the non-gasoline related products, but we have seen almost 40 to 50% in the gasoline related products. So this is something very important data set I thought to explain. Let's deep dive very quickly into what the data set has. The data set, the time series spans from January 1971 to June 2021, actually, and it is monthly data. We have 5 variables, primarily the year, month, and date. The consumer price index, which will be predicting and processing, and the item variable, which really specifies that what kind of consumer price index it is. On the right hand side, we see that there are almost 618 months of data for all the different categories. But in our data set, we'll mainly use the gasoline later on in the part four and five. So that's all about consumer price index data. A quick look at the consumer price index data shows that most of the categories have a simple trend increasing consistently from 1971 to 2021, which is almost close to 50 years. It is constantly increasing. But the two items, like gasoline and energy, has ups and downs. The interesting part, as you can see, the prescription drugs and the medical care has become so expensive as compared to other items, but um, we will deep dive into the gasoline data set for the time series analysis later on. In the part two, we will build the simple RNN model to process, train, and anyone predict the sine wave data set. Sine wave is nothing but a sine values of a continuous variable. which we plotted on a left-hand side, which just follows a particular pattern between two values, -1 and 1. So I have created 3000 such values for the base values of between 0 and 64, converted them into sine wave, and split the entire data set into three parts: training data set, which is almost 80% with 2400 records; validation data set, which is 10% and 300 records; and same way testing data set with 10% and 300 records. I have I have chosen to use the 50 values as a sequence in order to process the 50 values in history and predict the 51st value and so on. Uh, so let's discuss about the design of the simple RNN. I haven't designed the simple RNN just by selecting the arbitrary number of neurons. Instead, I have applied the grid search method, in which I have created a specific range of or values of the neurons which I want to pass through in my iterative function to build that many models. So I have actually built the 9 models with each having a different set of neurons in the RNN layer, and calculated the training loss and the validation loss for all of this model. As you can see on the right-hand side, the training loss actually is pretty consistent between neural networks with 100 neurons to 160 neurons and slightly increasing at 168. But the validation loss is pretty volatile. But we can clearly see that at 120 on a here also, it achieved the minimum validation loss. We did not use the training loss, but actually we used the validation loss. So we know that we are not selecting a model which is overfitting. So with that, I will go ahead and design the simple RNN neural network model with 120 neurons. As you can see, the rolled architecture shows the 120 neurons in the fully connected layer and one output and the input sequences. Whereas in the unrolled architecture, we can clearly see that 50 input sequences are fed into 50 RNN cells, which ultimately generates the one output state, which is fed into fully connected layers, and finally generates the output. So with keeping that mind, this particular architecture, we have trained the model for maximum 20 epochs. I have applied a method called early stopping, which keeps track of the validation loss when it hits the minimum and after a certain, patience value like, 5. If it does not stay at the minimum loss, it stops the training. So as you can clearly see, my model was supposed to train for 20, but I achieved the base weights and the minimum training loss and the validation loss at the 8th epoch. And that is where the training was stopped and the model was restored. So with that based model, I have tested that particular model to predict the values in the test data set, which model haven't seen, which is nothing but the continuation of sequence in the last 300 records. As you can see, almost there is no difference between the actual and the predicted values. The sample shows that the actual difference comes at the fourth decimal, which is very, very close to zero. So in summary, looks like simple RNN for a sine wave data set works perfectly well. Potential reasons could be the sine wave simple data set with the pretty definitive pattern, and it is very small data set, so RNN could have worked with a better accuracy. So with that, we understand how the simple RNN works and how it can be applied to the dataset, but there are some limitations of the RNN. As you can see on the top, we have an example called sentence, what time is it? Is it a very common sentence, right? We ask many times. But if you feed this sentence to the computer, how the RNN will process it will take a one word at a time, process it, and register a hidden state for that value, and learns to find out what the whether that information is important or not. And as it the model gets the further inputs from the sequence, it gets the states from the previous cell. But as it travels through the further into the sequence, the previous state's essence is reduced towards the later sequences. So as you can see, which I assume the final state of the RNN. The state of or essence of the what word has very minimal presence into the final state, whereas the just a question mark has almost 50% of the meaning into the final state. And that particular behavior causes the vanishing gradient problem. As you can see here, as RNN back propagation through the time works backward into the RNN cells, the gradient starts shrinking with all the values which it does not remember. And when it starts shrinking, um, it stops improving the weights. In nutshell, the neural network stops learning, and that is where RNN stops learning, and it does not really perform well when there is a long sequence. So with that, we can deep dive into the part three, which is all about LSTM. So what does LSTM mean? Is a long short-term memory. The RNN was a short-term memory, and LSTM actually remediates the limitations of RNN short-term memory by providing this architecture which tries to remember for a longer sequence, providing a long short-term memory. Um, and in nutshell, the LSTM cell is consisting of sigmoid activation, TANH activation, a cell state, which is nothing but a transport channel, a forget gate, input gate, and output gate. We'll deep dive into each of these in little bit detail. So let's quickly jump onto that. The sigmoid function, which is activation function, which shrinks the value between 0 and 1. And when it squishes the value between 0 and 1, basically what does it do? That it assigns the importance to the input signal and generates the output between 0 and 1. And the values close to 0 represents that it is not important, and values close to 1 represents that it is important information. It has a very specific use in LSTM, so that's why I wanted to quickly cover it. The TANH activation function shrinks the value between -1 and 1, and opposite to sigmoid. And the main purpose of this is that in neural network, when multiple values are multiplied, the values explode. And as values explode, it could create a different meaning when it is processed by neural network. So TANH is basically used to modulate the input values and output values going through the gates or the cells to keep them between -1 and 1. So with that, we'll quickly dive into what are the core components of LSTM cell. The major component of the LSTM cell is the cell state. This works as the actually memory of the LSTM, and it's a long-term memory because it's nothing but like a transport highway which carries the information from previous state to the next state without much modification. There are some modification happens, but it happens in terms of relevant information, and it mainly keeps the selective memory into the cell state. The mathematical function is represented here, which is nothing but the output from a forget gate is multiplied, and output from an input gate is added into the cell state. And we'll go into those in the next slides. So as you can see, the first gate is a forget gate. The forget gate basically processes the hidden state from a previous cell and the inputs, identifies whether the information is highly important or not, and based on that, it pointwise multiplies to the cell state, impacting the cell states to either forget some of the irrelevant information or keep the relevant information. And the mathematical function is shown here, and the output of the forget gate is nothing but a opposite name called remember vector, which is a vector of all the values based on the sigmoid output added to the cell state. Um, we'll go into the next gate, which is called input gate. The input gate, the main functionality of input gate is to really understand what the importance of the new input values. It processes the hidden states from a previous cell and the new input value at the current time stamp, determines what information is very, very important. And it also modulates the same output using the TANH function, multiplies that to output something called save vector, which which ultimately shows that what information from the input is really significant and what is not significant. And based on that, it adds that into previous cell states, and that becomes the current cell state. So with this, cell state is slightly modified, but or depending on what it is added, it becomes important or not important. Um, so with that, we'll go into the final output. The final output, again, the input and the hidden state from the previous cell are gone through the sigmoid function to identify what information is important. As the cell state has been modified multiple times, it is modulated using the TANH and pointwise multiplication done to really identify the final hidden state of the current cell, which will be fed into the next cell. The output is called focus vector. And this is the gradient descent process of the LSTM learning. I really wanted to quickly highlight that, however, it was not asked. Um, as you can see, we cover only one cell, but through the series of cells, when the input sequence goes and finally it generates the output, the back propagation goes through each of the LSTM cells in the entire LSTM layer. But as you can see, the back propagation happens on the cell state level, not at individual gates. And the gradient of error to the weights which are applied to the input and the hidden state using the chain rule, you can see that the gradient heavily depends on the gradient of the cell state, current cell state to its previous cell state. And the cell state doesn't really change a lot. The LSTM keeps it mainly constant. So in that case, the gradient of the cell state doesn't shrink to zero, and hence the gradient of the error to the weight doesn't shrink to zero. And hence, the weights are actually updated more frequently, and the LSTM keeps learning. And when it keeps learning, it remembers values from the previous and earlier cells, and that way it performs the better than the RNN and solves the vanishing gradient problem. So with that, we will go for we'll build the LSTM model to apply for the CPI dataset. As I previously covered, the CPI dataset contain a lot of different categories, but the gasoline price has some, time series variations. So I have selected that. And as the total data set was going from 1971 to June 2021, I did not have any real data beyond June 2021. So what I have done that I have reserved the last 12 months of data from July 2020 to June 2021 as my forecasting data set, and remaining I kept as a total data set for the LSTM data model. So as you can see, this 12 month of data, when it is going up, I have not taken in consideration, and we will see how it will perform. So in the first part, part 4, I have simply built a basic LSTM 6-layer model where I have 3 LSTM layers with the 50 neurons in each of them. Dropout layer with 20% dropout rate. Basically, it will set some of these neurons output to 0 on a random basis. So, it can provide better randomness to the learning process. And I have used the Adam optimizer, set the default 0.01 learning rate. I've used the 100 epochs to train this model with the batch size of 16. So ultimately, and the input sequence is of the 12 months and the batch size of 16. So basically, I'm taking the 12 input sequence for each batch and predict the 13th value in iterative fashion. So after training the model for 100 epochs, as you can see, the training loss dropped significantly from first to the second epoch itself, as you can see, drastically. And then the values were a little volatile up until around 60. And as you can see, around 63 or third epoch, it achieved the minimum loss, which is also very close to zero. And then it slightly changed all the way to 100th epoch. As you can see, the minimum loss at 63rd or 82 is not that much of difference than the 100th epoch. So basically, it looks like we have overtrained the model. If we could have stopped at 63rd itself, and will clearly see that this could impact the overfitting of the model. So let's apply the training, this train model, the test data set, the 300 training, not 300, sorry, the 61 values which we reserved into the training data set for the CPA index. We applied the train model and we try to predict those 61 values. If you plot it individually, it feels like that it is plotting the same sequence we have seen earlier. But when we plot it on top of the original value for the peer-to-peer comparison, we can clearly see that it is almost following the same trend of the original value. Um, so this model is pretty accurate, and the potential region is the very small data set and not a complex model. I have acquired the mean square error for the 61 data set values and the root mean square error just to compare for the model performance in the next sections in part 5. So we'll keep these values in mind and we'll come back to that. So this is all about tasting data set. As we previously covered, we have also reserved the 12 month of data between July 21st to July 2020 to June 21st for the forecasting problem. So in the forecasting time series problem, what we'll do that we'll take the previously trained model and just retrain that for additional 20 epochs. As you can see, again, the loss starts from 0051 to go to all the way to 0023, which is much below than the training loss which we previously achieved here at the 0034. So I stopped training at the 20th epoch because it was difficult to continue training beyond that. And we also achieved the minimum loss with MSE of 737 and RMSE 27, which is better than the test RMSE, which we just saw in a previous slide. And based on that, I have forecasted that 12 month of CPA values of gasoline. And individually, if you plot as extension to the previous data, it just shows the sharp increase, upward trend, which was not there, right? We had some jiggling values there. If you plot that just 12 month of original value and 12 month of forecast data, yeah, it shows the upward trend. But there is a bigger gap here. It did not capture the dip between the July to November 2020, and then beyond November 2021, it seems to matching. So when you consider this, it generates the mean error of 30 points for the values of 200 to 280, which is significant, like close to 15% error rate. So the forecasting really doesn't provide the best result, and there could be a lot of potential reason for that. Specifically, as we can see, COVID was one of the outlier here when the gasoline price decreased because of the traffic, and then suddenly supply chain issue caused that to rise. The simple forecasting does not account for that. This could be a multivariate problem, which should account some of the other patterns, but will not cover here. So in order to uh, see how we can improve the performance, we'll redesign the LSTM model for the same CPI data. In order to redesign the LSTM model, again, I have applied the grid search method. I have used the different values of the number of neurons and different values for dropout rate. And I have created 12 combination, basically 12 models to apply on the original 6-layer LSTM model. And in my function, I'll pass the number of neurons from the first column and dropout rates from the second column across all the layers and see how it performs for the training and validation data sets. Um, I have also tried one more model, which is the 8-layer LSTM model with 2 more layers, one LSTM and one dropout layer. But I have kept them as the 50 neurons like my previous original model and 20% dropout to see how it performs as compared to the previous model. And I have run that through iteration, and this is the output of all the iteration. As you can see, I have a 13 outputs, and I have number of layers here, 3 and the one with 4, number of neurons, dropout rate, and the training loss and the validation loss, the minimum values. As you can see, this highlighted record has the minimum validation loss of 0.005 and also minimum training loss with this entire method. And as I use the 10% of validation data set, I can confidently say that with this combination of 100 neurons and 10% dropout rate, potentially this model is not going to overfit. As you also can see that this model took almost 80 epochs to train, so it did not converge very quickly and it did not took a long time to converge. So we'll use this model. So ultimately, I have used that model, which is nothing but essentially the three-layer model with 100 neurons and a 10% dropout. The summary shows around 200,000 parameters it will train in the overall in this model. And the summary of all the layers can be seen here. Adam optimizer, default learning rates, and we'll again train for 100 epochs, but the training will stop based on the early callback method. And we predicted the training and validation loss. As you can clearly see that even though I specified 100 epochs, the actually training stopped almost at the 43rd epoch. The training loss, the minimum training loss was achieved on the 29th epoch of 0.0026, and the minimum validation loss was achieved at around 33rd epoch of 0.0082, which is not significantly different than the last epoch. So this model is basically restored to use the weights as of the 33rd epoch. And I will be using that to apply that to the testing and forecasting data set like I previously did. Um, so let's quickly go over the testing and forecasting performance. As we have seen previously in the original model, looks like it is following a pattern, but it is not following the same pattern as the original model. Also, the RMSE and the MSE value, the mean square error and the root mean square error has increased significantly. Previously, we saw 30 and some change. Here we saw 35 and some change over the mainly the values around 200. So the percentage has increased in terms of error. So it seems that this model did not really perform well as compared to my original model, but not too bad also. So still, I'll go ahead and use that model to forecast and see how does it perform. We repeated the same method. We used the July 2020 to June 2021 dataset and retrained the previous model with 100 neurons and a 10% dropout rate. As we can see, again, the loss dropped and then it started stabilizing towards the end, not changing significantly in the third decimal places. And we registered the minimum loss at the 30th epoch, which was around 0.0014, and even the last loss was also 0.14. So this model is not overtrained. It did the early stopping, and it achieved the RMS of 27, which was pretty comparable to the previous models. But if you really plot this data onto the graphs, specifically this graph, as you can see, um, uh, the trend is worse than the previous model. At least in the previous model, it was consistently increasing, but here it is crossing over the original value. It is not covering the proper prediction here with the polynomial curve, and it is going down in the later portion. This model again proves that this model did not perform well as compared to the original model. So with that, I will quickly compare the performance, which we already compared, but I'll go through the slide. As we see, the original model was both three layers, two dropout layers. The only difference was number of neurons and the dropout percentages. So with that, these are the difference between the architecture of both the layers. And these are the difference between the tasting data set for the original model and the redesigned model. We can clearly see that the original model performed well from the statistic perspective and the visual perspective also. with the lower RMSE and the pretty good matchup on the graph versus this one. Um, we can compare the forecast also. We already talked about it. That RMSE is pretty comparable, but somehow, the trend is not captured into the latest model, and shows the wide variance, whereas the original model was pretty much following the trend, with the exception here. And as we already outlined, that forecasting is difficult challenge, and we'll cover that in the conclusion. So here we are at the conclusion. As we see, RNN and both LSTM can be used for predicting and forecasting sequence data. RNN suffers from the vanishing gradient due to the short-term memory, and LSTM can overcome that with the help of cell state as information transport channel, and gates can be used to determine which information is important and which is not. The back propagation and the gradient descent calculates the cell state, which is moreover constant and doesn't shrink to zero, and that's why the LSTM is ideal choice when it comes to predicting the longer sequences. Talking about our learning from the model training, we clearly see that the number of neurons participating in design making process in all the layers, and even the number of layers play a bigger role to drive the model accuracy and complexity. It does not. It is not always true that the higher complex model will always perform better. We clearly see that when we increase the number of neurons from 50 to 100 and reduce the dropout rate from 20% to 10%, it actually performed worst. So it is not always true that the increasing number of neurons and layers will always perform better. Also, we learned that model should not be trained beyond certain limit. It has high potential to overfitting and may not perform well with the newer data. And finally, the forecasting numerical value purely based on just a time series sequence may not be a good idea to, because it may not perform well as expected. There are additional variable needs to be always accounted for the predicting the LSTM. Sorry, any sequence data or time series data. Otherwise, we could have perfectly predicted stock price and cryptocurrencies. So with that, I want to conclude my final presentations. I know I went over 32 minutes. I'm extremely sorry for that. And I really enjoyed this class, and thank you very much, Professor Tuan, and everyone for your support and great learning. Thank you, everyone. Bye-bye.